So we're going to talk a little about work, potential energy, and universal gravitation. Just to remind you, the formula for work is force times distance times the angle between those two things, right? We can also say the work done by gravity is minus the change in the potential energy. That is to say, when an object is being lifted, the work done by gravity is negative the change in its potential energy. This person lifted this object to a height h, and so they did mg times h to get it to that high. And while that was going on, gravity was pushing the opposite direction. And so if we did an mg cosine theta, we would get the work by gravity is equal to minus mg times h, because gravity is pushing down while the object was moving up. Right? So if we kind of put all this together, we can say, look, if we're just talking about vertical motion, we can get rid of the cosine and replace it with a negative sign here. And that means that the work done is negative when the object's being lifted and positive when the object's being lowered. That's what the minus sign does. And that's equal to minus dPe. So I have to replace the deltas with the calculus-y version of d. And I say, look, for an incremental amount of work done, that's just F times dy, where dy is how high you lifted it. In just a minute, I'm going to change that to a dr. And that's equal to the incremental change in potential energy. I can just look at these two terms and cancel the negatives, and I get the change in potential energy is the force of gravity times dy. And so that says the force of gravity is equal to dPe, the change in potential energy with respect to height. If we use r instead of y for our vertical direction, we can just rewrite this dPeg. So the incremental change in potential energy with respect to r, which is now our vertical variable, is equal to the force of gravity, which is gmm over r squared. And you don't have to know much calculus to be able to figure out that this quantity, when you take its derivative with respect to r, gives you this quantity. And so we don't need a proof for that, but you can just check it, right? G, mass of the Earth, and mass of the object are all constants, and so I'm just taking the derivative of 1 over r, technically negative 1 over r, and that just gives me 1 over r squared. And so in a world where this represents the force due to gravity, this represents the potential energy due to gravity. So now that we know the formula for the potential energy, we can do an escape velocity problem. And we can say, what is the escape velocity for an object on Earth's surface? The escape velocity is how hard you have to throw it for it to completely escape Earth's gravity. In other words, get to r equals infinity, right? And the least velocity you have to give it gives it a velocity of 0 just as it gets infinitely far away. And so this is our formula for potential energy. And when we know that when r goes to infinity, the potential energy goes to 0, right? As this r gets very large, the potential energy becomes 0. If the kinetic energy is 0 at this point, as we just said, then we can use this formula, conservation of mechanical energy, that says, the potential energy plus the kinetic energy on the Earth's surface is equal to the potential energy plus the kinetic energy at infinity. Well, these two guys are both 0, right? That guy's 0, and that guy's 0 at infinity. The potential energy is 0 because of this formula. The kinetic energy is 0 because if it was any more than that, if it was positive, then we would have given it too much energy to escape. We want to find out just how much it needs to leave, right? And so that means all that's left is there's a 0 on the right-hand side in these two terms. And so that says the initial kinetic energy, it's kind of what we're after, is equal to minus the initial potential energy. Well, that means 1/2 mv initial squared is equal to the negative of the potential energy initially, and that's the initial potential energy is minus g, mass of the Earth, mass of the object you're throwing over the radius of the Earth, right? A negative sign on the outside for that one and one on the inside for that one. And so I get this formula. I get the velocity is equal to the square root of 2g mass of the Earth over the radius of the Earth. And so if we evaluate that, the velocity is the square root of 2g times mass of the Earth over the radius of the Earth. If I plug in all these numbers here, I get about 11.2 kilometers per second, or 11 miles per second. That's how hard you have to throw an object to leave the surface of the Earth. It's different from, launching a rocket, right? We're just pushing the whole time. This is just saying, what does its initial velocity have to be for it to get off if you're just going to fling it off? There are a couple things to notice about this. First, notice that even if I don't change the mass, if I make the radius smaller and smaller, the escape velocity has to get bigger. And so for compact objects like neutron stars, they generally have a very large escape velocity. And this is kind of what defines a black hole. When the escape velocity is greater than the speed of light, then if this r is so small that the escape velocity is greater than the speed of light, then light can't get off the surface of the object, and that's why it gets called a black hole.